Okay, so starting off with the diagram, we have our planet with the same radius as Earth, 6,371 kilometers, and we have a payload that's in orbit with a distance of 7,200 kilometers, including the radius of the planet. And so that's our diagram right now. So the first thing we did was figure out how to derive centripetal force. What we did was we realized since it's going at a circular orbit, we could utilize a little bit of physics, but in order to do that, we found that the difference in the two velocities at 2 points along a circle, when you're deriving it, you can create a similar triangle that basically creates what the actual delta velocity is, and from there, you find that delta V is the difference in VF and VI. So VF in by definition is VI plus delta V, I mean. And so from there you figure out that that is what your velocity final is, and because of that, acceleration is just the change in velocity over time, which is your velocity squared over the radius, and with that you get acceleration centripetal.
And so basically, there are two main forces that are important to keeping an object, in this example a payload, in orbit, and that is the centrifugal force, which basically keeps the object away from the planet, and the gravitational force, which pulls it down. And so in order for something to stay in orbit, these two have to be balanced, which is why we set these equal to each other. We found out that these two forces basically have the same formula, which is how this came around. And since they are the same, then the centrifugal acceleration or speed equals the gravity, which is 9.8. And so taking the equation that we derived from there, we set this equal to 9.8 meters per second squared. And by plugging it in and multiplying it by the distance, which we got from here, the distance from the orbit to the center of the planet, we got to 7.056 times 10 to the 7th. And taking the root of it, we found the tangential velocity to be 8,400 meters per second.
Okay, so for part 2 of this problem, it's asking for what angle theta should we launch the payload from the surface of Earth. So we figured out that the easiest way to get the object in orbit is to directly counteract the force of gravity. Because there's no atmosphere, the only thing that's acting against this payload is the force of gravity. So to be the most efficient, you would shoot it exactly upwards, like in this picture, with an angle of 90 degrees with respect to the horizontal, because that will directly counteract the force gravity that's acting downwards.
So step 3 basically asks us to solve for the time it takes for the object to go into orbit. And so basically we started with the derivative of the velocity, which gives us the acceleration. And in this case, it is gravity. And it's negative because gravity is basically a downward force. And so from there, we basically integrated both sides and got into this kinematics equation, which we will use to eventually find the amount of time it takes. And so plugging in what we have, we put in 0 for the final velocity because an object that is in orbit basically has a velocity of 0. And we plugged in 10, which is the initial velocity given to us in the problem. And we plugged in 9.8 for the gravity over there. And so from there we basically solved for t and got to 17 minutes.
So referring back to our original sort of diagram, we have this distance that's the radius of Earth, which is 6,371 kilometers, and we know that the radius plus the amount of orbit, the distance that the object orbits, is 7,200 kilometers. So the distance traveled should just be the 7,200, which is the total, minus the radius, and that will give you this little piece right here, which is the distance that the payload traveled, which is 829 kilometers.